Good evening everyone. Good evening. I welcome you all again to the NEET Elite. Hope you guys are doing great, having the good time. Well people, let me know in the chat box if I'm audible and visible to everyone. Let me know in the chat box if I'm audible and visible to everyone right here. Good evening everyone. Good evening. Welcome to the session. Welcome guys. Welcome back. Yes, the army is back. Yashwant has again come up with a quote. Security is mostly a superstition. Life is either a daring adventure or nothing. Great. Good evening. That was great, Yashwant. That was great. Keep on coming up with these great quotes, these motivational quotes here. Chiranjeevi, there will be 3 more sessions apart from this session from this chapter. Yes, absolutely. I'm not going to leave anything in this chapter. It's really very important one. Right? After this session, after this, in the next session, we are going to talk about the kinetics of reversible and parallel first order reactions. And then we'll be moving to the Arrhenius equation. Yeah? Yes? Okay. So people, let me know. This is going to be our 4th session from the chapter Chemical Kinetics. Yes. And in the today's session, what we are going to talk about is we are going to talk about the rate constant for a first order gaseous phase reaction. Okay. And apart from there are many interesting things which we are going to talk about in the today's discussion. It's going to be most important session from the chemical kinetics point of view. Okay. So whatever I'll be writing on the screen from the beginning, do note everything over here. Okay. Whatever problems I'll be giving you, note them down, because those are going to be really important. In every question there will be a nice concept involved in every single question. Yeah. Okay, so before starting the session, people, let me introduce myself. As you must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Yes. Okay, so before starting the session, let me give the brief introduction about the NEET 2021 crash course which we have started on the actual Vedantu platform apart from the YouTube sessions. Yeah. Okay, on the actual Vedantu platform, we have started a NEET 2021 crash course in which we'll be personally mentoring you, will be personally helping you out in qualifying the NEET 2021 examination with a good rank. Yes. And people, in order to be part of this NEET 2021 crash course, there's a link given in the description box of the video. Just click on that link. Okay. And let me tell you what all benefits you will be getting in this crash course. So first thing, we are going to cover your whole syllabus before your NEET 2021 examination. Yes. Apart from that, there will be test series, right? There will be mock tests. By means of which you'll get to know your overall performance and you can compare your performance with the other students across the country. Yes. So it's going to be highly beneficial for you. Trust me on that. Okay. And people, there will be, apart from the syllabus completion, there will be some separate sessions on the time management. Okay. And there will be sessions on the amazing tricks and tips by means of which you can solve the questions in lesser time as well. And definitely it's going to be a two-way learning interactive platform. Okay. And you can ask your doubts anytime to your master teachers. They'll be available for you 24/7. Yes. And if you want me to personally train you, what you guys have to do is you just have to click on the Vedantu app on your phone or laptop, wherever it is. Yeah. Just click on the NEET crash course. After clicking on the NEET crash course, you just have to use the coupon code as WSCC21. And on using this coupon code WSCC21, I'll be mentoring you personally for your chemistry. And apart from that, you'll be getting the 20% off right here. And you're just getting this crash course for 8K. Yes. In this 8K, your entire syllabus, okay, test series, mock tests, everything will be provided to you. Okay. So do get enrolled in this and do not forget to use this coupon code right here. So people, there's a link in the description box of the video as well. You can enroll through that as well. Just click on the link which is there in the description box. Click on enroll and just get enrolled. Yeah. And for the ones who have not liked the video yet, do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Yes. So people, these are the things which we are going to talk about in the tonight's session. Well, we'll be starting from the different characteristics of first order reactions. A lot of characteristics of first order reactions we have studied in the last session, if you remember. yes, in which we talked about the degree of dissociation, how to calculate degree of dissociation in case of a first order reaction. Yes, a lot of many things we talked about in the last session, which were basically the characteristics of the first order reaction. And there are few more characteristics of first order reactions left, and we are going to cover them first. Then we'll be moving to the rate constant for a gaseous order reaction, for a first order gaseous reaction. And there are going to be definitely some good questions which will help you out in clearing out the concepts as well. Yeah. Okay. Right. So people, super excited, damn excited for this session. Let me know in the chat box. Yes, I cannot see the Josh, guys. Let me see the Josh first. Yeah. Super duper excited for the session, right? Super duper excited, question mark. Okay, that's wonderful. Now that's great. Now that's great. Yeah, that's wonderful now. Okay. So people, let's get started with some important characteristics of the first order reactions right here. Okay, few of them we have completed in the last session, few of them we'll be completing right now. Okay, now understand properly what I'll be saying. Okay, these are really going to be very important. See guys, for example, I'm taking a first order balanced chemical equation. Let's say I've got a balanced chemical equation right here, which is of the order 1. It is the first order reaction which I'm taking right here, okay? And I'm assuming the reaction is balanced at the same time, right? Okay, let's assume the rate constant of the reaction is K, okay? At time t is equal to 0, guys, we know the concentration of reactant is represented by A0 and concentration of product is represented by 0, yes? Now, what is going to happen to the concentration of reactant with time? Concentration of reactant with time is going to decrease, yes? So people, at any time t, let's assume the concentration of reactant left is AT. Let's assume the concentration of product formed at time t is BT, yeah? What is AT right here? AT is the concentration of reactant left at time t. What is BT? BT is the concentration of concentration of product formed at time t. And what is this A0 right here? A0 is the initial concentration of reactant over here, yes? Now people, the first thing which I'll be doing right here, if I will write, since I have assumed the reaction is of the first order, if I'll write the integrated rate equation for this first order reaction, how it's going to be, understand. I'll write simply rate constant of the reaction is equal to 1 divided by T, ln of initial concentration of reactant, which is A0, divided by concentration of reactant at time T, which is AT, yes? And at the same time, guys, if you remember in the last session, we talked about the half-life of the first order reaction as well, right? And the half-life of the first order reaction used to be equal to simply T half is equal to ln of 2 divided by K, yeah? Or I can write that like this, K is equal to ln of 2, K is equal to ln of 2 divided by T half. I can write the same equation in this manner as well, yeah? Now people, if I'll compare these two equations right here, I'm going to get one important result, okay, which will help you to solve the equations easily right here, okay. Now what I'm going to do right here is, I'm going to compare these two equations right here. K is equal to this, K is equal to this. That means I can clearly say ln of 2 divided by T half, ln of 2 divided by T half, this should be equal to 1 divided by T ln of A0 divided by AT. Yes, this is the equation which I got right here, correct? Now people, what I'll be doing right here, see, I'll be just shuffling the equation a bit, I'll be just rearranging the equation a bit so that I get a proper result which we'll be using directly in the questions. So take this T over here in the numerator, it's going to be T divided by T half, ln of 2 should be equal to, I'll be writing it as ln of A0 divided by AT, definitely, yeah? Now guys, what I'll be doing, can I write it something like this, ln of 2, this term I'm going to take as the power of 2, it's going to be T divided by T half, I can write it like this as well, no issues, yeah? It's going to be ln of A0 divided by AT, correct? So people, ln of something, I can simply get something like this, 2 to the power T divided by T half is equal to A0 divided by AT, correct? Now this term which you are seeing right here, this T divided by T half, I'm going to represent with another term, T by T half, I'm going to represent with another term N, where N stands for number of half-lives. N stands for number of half-lives right here. Yes, and what is this number of half-lives all about? You'll get the idea in some time, right? Okay, now I can write something like this. 2 to the power n is equal to a naught divided by 80, correct? Or people, I'm going to get one important result right here. I'm going to get it like this. 80 is equal to a naught multiplied by 1 divided by 2 to the power n. This is one important result which is only valid for the first order reactions, okay? Very simple, understand. What is this 80 going to be? I'm going to use this equation in order to calculate the concentration of reactant left at any time t. Whenever I'll be asked to calculate the concentration of reactant left at any time t, I'll be going with this equation. 80 represents the concentration of reactant left at any time t. A naught is the initial concentration of reactant, and this n is what we call as number of half-lives. And what are these number of half-lives all about? Understand. For example, guys, this is the first order reaction which I've taken right here. Yeah, this is the first order reaction which I've taken right here. Let's assume its half-life is equal to 10 minutes. Let's assume its half-life is equal to 10 minutes. Yeah, its half-life is equal to 10 minutes. This is what I'm assuming right here. Okay, right? Now what I'll be doing over here is, let's say I'm writing time t is equal to 20 minutes. Can I say time t is equal to 20 minutes means 2 half-lives? If I write time t is equal to 30 minutes, can I say 30 minutes means 3 half-lives? Yeah, so n simply represents the number of half-lives over here, which is going to be given time t divided by t half. So 20 divided by 10 is going to be 2 half-lives. If the given time was 30 minutes, that means 3 half-lives, 40 minutes, 4 half-lives, 50 minutes, 5 half-lives, and so on. Yeah. Now, how I'll be using this equation in the questions directly? Understand that right now, okay? It's going to be very important, guys, okay? All right, let's get started with the questions in which I'll be using this equation over here. The first question which is on your screen, guys. The first question which is on your screen, okay? What is mentioned in the question? K, rate constant for the first order reaction, is given as 1.386 minute inverse, yeah? Rate constant for a first order reaction is given as 1.386 minute inverse, right? Calculate the concentration of reactant left after 8 minutes, right? Let's say I've got the first order reaction as A gives B. Let's say this is my first order reaction whose rate constant is K, right? It's first order right here, correct? Let's assume at time t is equal to 0, the concentration of reactant is A naught, the concentration of product will be 0, yes? Now people, we know at time t, the concentration of reactant left is represented by AT, the concentration of product formed is represented by BT, yes? Now what are we supposed to check? We are supposed to check after 8 minutes. What will be the concentration of reactant left? So at time t is equal to 8 minutes, we are supposed to calculate the value of AT. That's what we are supposed to do, yeah? After 8 minutes, what is going to be the concentration of reactant left? So we are going to calculate the AT value at time 8 minutes right here. Okay, how will I be approaching to this sort of equation? Correct? Now people, the first thing which I'll be doing right here is, say, I'm given with the rate constant of this first order reaction, right? If I'm given with the rate constant of first order reaction, which is 1.386 minute inverse, yeah? Can I calculate the half-life of this first order reaction? We know the result, yeah? We know half-life of the first order reaction is nothing, that is 0.693 divided by what? Divided by K. K value is 1.386 minute inverse. So the value will be simply 1 divided by 2. 1 divided by 2. So 1 divided by 2 minutes is going to be the half-life of this reaction. Yes. 1 divided by 2 minutes is going to be simply the half-life of the reaction, or you can write that as 0.5 minutes, right? Okay. Now people, I got the half-life of the reaction. Now, at what time we are supposed to calculate the concentration of reactant left? We are supposed to check at time t is equal to 8 minutes. After 8 minutes, what is going to be the concentration of reactant left, right? People, can I write something like this? N, number of half-lives, which few minutes back I told you that's going to be t divided by t half. Correct? What is the t value given to me? T value, time is given to me as 8 minutes divided by half-life we got as 1 by 2. So the value is going to be equal to 16. So right here, that means this 8 minutes means over here that the reaction has completed 16 half-lives till now, okay? I got the value of n. Why did I calculate the value of n right here? In order to use the equation, AT is equal to A naught multiplied by 1 divided by 2 to the power n. Yes? Correct? Now people, after time t is equal to 8 minutes, what is the concentration of reactant left? This AT represents the concentration of reactant left after time t is equal to 8 minutes, which is going to be A naught multiplied by 1 divided by 2 to the power n. N value I got now simply 16. So this is going to be your answer right here. So this is going to be the concentration of reactant left at time t is equal to 8 minutes. This is the concentration of reactant left after 16 half-lives right here. Let me know in the chat box if you got the concept properly. Let me know in the chat box if you got how to solve this sort of equation by means of this equation. Let me know in the chat box with the thumbs ups. Yes. Yes, Shaista, you're absolutely right. Yeah. I want everyone to say it if it is clear or not, so that I can move ahead and talk about a few more interesting things right here. Yeah, it is done. It's done. Wonderful. That's great. Yeah. Cool. Let's move on. Let's move on to one more question then. Which is given to us right here. What amount of reactant will be left after 3.5 minutes? And curve for a first order reaction is given to us. This is the curve for a first order reaction which is given to us. Yeah. Okay. What amount of reactant? We are supposed to calculate the concentration of reactant left after 3.5 minutes. Yeah. Concentration of reactant left after 3.5 minutes. Correct? How we are going to approach to this sort of equation? Again, it's a very simple thing. See, since the curve is given for a first order reaction, people, if you remember, in the last session, I gave you one equation for the first order reaction that was integrated rate equation only. That was ln of AT is nothing that is equal to ln of A naught minus KT. I hope you remember this equation. Yes, correct. Can I say this curve is just between ln of AT versus T right here, and ln of AT I've plotted along y-axis and time I've plotted along x-axis. Yes. So instead of ln of AT, you can write y. Instead of time, you can write x. And before this is going to be m. Sine over is minus, and this is c. Y is equal to minus mx plus c. So the curve is a straight line with a negative slope. Yeah, this is the curve which is given to me. Correct? Now, people, what is the slope of this curve? Slope of the curve which is given to us is equal to minus k. Yeah, I hope you get it. Slope of this curve which is given to me is equal to minus k. What is slope? Basically, slope is nothing. Slope is tan of theta. So tan of theta value is given to us as minus k. And what is this theta right here? Theta is the angle which the curve makes with the positive x-axis in anti-clockwise direction. This is theta right here. Correct? This is theta. And people, if this is 45, this is 90, this will be 45. That means this angle is going to be simply 135 degrees right here. Now people, tan of 135 is simply minus 1. So I can write minus 1 is equal to minus k, or k value you'll be getting as 1 right here. And what are going to be the units of k? The units of k are going to be minute inverse over here. Yes, I got the unit of k right here. Oh, sorry, I got the value of k right here. Yes, the rate constant value I got right here by using the curve. Correct? Now guys, after getting the value of k, I'm going to calculate the half-life of this first order reaction, as you all must be knowing, which we know T half is equal to ln of 2, and it's mentioned in the equation. Take the ln 2 value as 0.7 divided by k. K value I got simply as 1. So I got the half-life as 0.7 minutes. I got the half-life of the reaction of the first order reaction as 0.7 minutes right here. Yes. Now people, if you got the half-life of this first order reaction, what am I supposed to calculate? I'm supposed to calculate the concentration of reactant left after 3.5 minutes. Yeah, correct? I'm going to represent it like this. Let's say I've got a reaction as A gives B. It's of a first order reaction. At time t is equal to 0, the concentration of reactant is represented by A naught. The concentration of product will be 0. Yes, at any time t, the concentration of reactant left is represented by AT. Yes, and now what am I supposed to calculate? I'm supposed to calculate after 3.5 minutes. After 3.5 minutes, what is going to be the concentration of reactant left? So I need the value of AT after 3.5 minutes. Okay, so first thing which I'll be checking right here, I'll be checking this 3.5 minutes means how many half-lives. 3.5 minutes means how many half-lives, and number of half-lives we know that is given time divided by half-life. Given time is given to us as how much? It is 3.5 divided by half-life is nothing, that is 0.7. So n value over here you got as 5. Correct? Number of half-lives you got as 5. Correct? Now people, after this I'm going to use the equation which I derived a few minutes back. What was the equation all about? Equation was simply concentration of reactant left at any time t is equal to A naught multiplied by 1 divided by 2 to the power n. This is the equation which we derived a few minutes back, right? Now people understand. Now people understand. We are supposed to calculate the concentration of reactant left after 3.5 minutes. So this 80 right here, it represents the concentration of reactant left after 3.5 minutes, or I can say this 80 represents the concentration of reactant left after 5 half-lives. It's going to be A naught divided, multiplied by 1 by 2 power 5. 1 by 2 power 5. 2 power 5 means simply 2 to the power, so or let me write it like this, 2 power 5 means simply 32. Yes. So can I say this is going to be the concentration of reactant left after 5 half-lives? Yes. Or I can say this is going to be the concentration of reactant left after 3.5 minutes. Yes. I hope this is clear to everyone. Let me know in the chat box. Let me know in the chat box if it is clear to every single guy right here. Yes. Let me know in the chat box, guys, so that I can move on and talk about few more interesting things right here. Yeah. Yes, Vinay, redox reactions is completed fully. Yeah. All right, Radhika, fine. I'll be doing that for you. Okay. Last step is nothing. N value I got 2 to the power 5 means 32. So it's going to be A naught by 32. That's it. Yeah. Okay. Let's move on, guys. Let's move on. And let's talk about one more important thing right here. This is going to be one more important thing from which a particular type of question is asked in your examination. Okay. And what is that question going to be? In order to do that question, I'm going to give you the concept first of all. Okay. See, guys, what I'll be doing right here. I'm going to calculate the expression of rate constant. I'm going to calculate the expression of rate constant. I'm going to give you the expression of rate constant when two different concentrations of reactants are given at two different times. I'm going to give you the expression for rate constant when two different concentrations of reactants are given to me at two different times. Yeah. How is that going to be? Understand. Let's say I've got a reaction, I've got a first order reaction as A gives B. This is my first order reaction right here. This is my first order reaction right here, whose rate constant is nothing, it is equal to K. Yeah? Correct? Now we will see. At time t is equal to 0, understand what I'll say. At time t is equal to 0, let's say the concentration of reactant is A naught. Concentration of product will be 0, right? Now with time we know concentration of reactant will keep on decreasing. Concentration of reactant will keep on decreasing. Let's say at time t1, the concentration of reactant left is equal to AT1. Yeah. Now similarly, the concentration of reactant will still keep on decreasing. Yes. Let's say at time t2, the concentration of reactant left is equal to AT2. Right? Right? Now guys, see what I'll be doing right here. See what is going to be important right here. First thing, if I'll say from time t is equal to 0 to time t1, that means I'm talking about this time interval t1, right? In the time interval t1, the concentration of reactant is changing from A naught to AT1, yeah? And in the time interval t2 means time is equal to 0, time t is equal to 0 to t2. In time interval t2, the concentration of reactant is changing from A naught to AT2, yeah? Yeah. Now people, what is going to be the time interval in which the concentration of reactant changes from AT1 to AT2? The time interval in which the concentration of reactant changes from AT1 to AT2, that is simply going to be T2 minus T1. T2 minus T1 is the time interval in which the concentration of reactant changes from AT1 to AT2. Yeah. Correct? I hope this is clear. I hope this is clear. Yeah. Now we will have a look. What I'll be doing right here is understand properly. See, first of all, I'm going to write the integrated rate equation at time T1. If I write the integrated rate equation in the time interval T1, what it's going to be? I'll write K is equal to 2.303. I'll write K is equal to 2.303. Correct? 2.303. Divide by what? Or let me write simply like this. Just a second. I'll write something like this. T1 is equal to 2.303 divided by K. It's going to be log of initial concentration divided by concentration of reactant left at time T1. Initial concentration is A naught. Concentration of reactant left at time T1 is nothing, that is AT1. Correct? This is one equation which I formed right here. Yes. Now people, similarly, I'm going to write one more equation in the time interval T2. I'll say T2 is going to be equal to 2.303 divided by K. It's going to be log of initial concentration of reactant, that is A naught, divided by concentration of reactant left at time T2. What is the concentration of reactant left at time T2? That is AT2. Yeah, that is AT2, correct? Yes, let's call this as equation number 1. Let's call this as equation number 2. Now, people, what I'll be simply doing right here is I'll be subtracting the two equations. I'll get one important result right here. I'll be doing equation second minus equation first. Equation second minus equation first, it's simply going to be equal to what? It's simply going to be T2 minus T1. T2 minus T1. I'm going to take 2.303 divided by K, 2.303 divided by K as common on both the sides. Yeah, it's going to be 2.303 divided by K. I took it as common, correct? Log of what? Log of this term minus log of this term. Log of M minus log of N. That's going to be log of M divided by N. So it's going to be log of M divided by N. M is nothing. M is A naught divided by AT2. Log of M divided by N. N is nothing. N is A naught divided by AT1. Yes, it'll be something like this, correct? Can I say this A naught and A naught got cancelled right here? So I got one important result right here. Just take this K out over here. Just write it like this. K is equal to 2.303 divided by T2 minus T1, and T2 minus T1 is the time interval in which the concentration of reactant changed from AT1 to AT2. It's going to be log of what? Log of A T1, which is the concentration of reactant at time T1, divided by concentration of reactant at time T2. This is one important result which I'll be using directly in the questions. And when I'll be using this result, let me tell you guys, whenever you are given with the concentration of reactants at two different times, at that time you are going to use this expression in order to calculate the rate constant. Yeah, number 1. Number 2, guys, number 2, let me erase this part. I hope this is clear till here. Yeah, let me erase this part. Now, people, since it is a first order reaction, so as per the rate of reaction, as per the rate law is concerned, rate of reaction is going to be equal to K multiplied by concentration of A to the power order, that is 1. Yes. Now, guys, if I will write the same equation at time T1, at T1, let's assume the rate of reaction is R1 is equal to K multiplied by what is the concentration of A at T1? It's going to be AT1, correct? Similarly, if I want to write the rate of reaction at time T2, which is going to be R2, R2 is the rate of reaction at time T2, it's going to be K multiplied by concentration of reactant at time T2, which is AT2, yeah? Correct? Now we will have a look. If I'll divide these two equations, can I get something like this? R1 divided by R2 is equal to AT1 divided by AT2, correct? So what I'll be doing right here is I can make one more expression in terms of rates right here. AT1 divided by AT2. Instead of it, I'll be writing R1 divided by R2. So people, I got one more expression right here. Rate constant is equal to 2.303 divided by what? Divided by T2 minus T1. It's going to be log of, instead of AT1 by AT2, it's going to be rate of reaction at time T1 divided by rate of reaction at time T2. This is the expression which I'll be using in the first order reactions when the rates of reactions at two different times are given to me. Yeah. Okay, these are two very, very important expressions which I'll be directly using in the questions. Let me know if you got the expression so that I can move on and give some questions based on this. Yeah. Let me know in the chat box fast. Yeah. Is it noted? Yes. So let me have some water first. Yes, Yashwant, I'm having some dihydrogen monoxide. Yeah. Thank you, Mr. Khan. Okay. Gayatri, I'll be conducting mock tests maybe day after tomorrow, yeah? Yes, day after tomorrow I'll be conducting the mock test, yeah? All right then. Let's move on and let's do a question based on the concept which I gave you right now, okay? The question was asked in IIT 2001 when I was in first standard, yeah? But the simple question, guys, if you know the expression which I gave you right now, if you can use that expression properly, you can solve this question in less than 10 seconds as well. But I'm going to give it slowly, yeah? I'm going to do it slowly, correct? All right. See, the rate of the first order reaction is 0.04 moles liter inverse per second at time t is equal to 10 minutes, yeah? And 0.03 moles liter inverse second inverse at 20 minutes. Yes. So people, the first thing, am I given with two different rates at two different times? So I'll use the concept which I gave you a few minutes back. Yes. Now what is given in the question? Understand properly. See, the rate of the reaction the rate of the reaction is 0.04 moles liter inverse second inverse at what time? At time t1 is equal to 10 minutes. Yes. And people, at the same time, the second rate is given as, which I'm representing by R2, the second rate is given as how much? It's given as 0.03 moles liter inverse second inverse at time how much? At time 20 minutes. Yes, this is something which is given to me, correct? This is something which is given to me. What am I supposed to calculate? Find the half-life of the first order reaction right here. Find the half-life of the reaction right here, okay? We are supposed to calculate the half-life. I'm first of all given with two different rates at two different times. So I'm going to calculate the half-life. In order to calculate the half-life of the first order reaction, I should know the rate constant value. Yes. So my first thing right here is going to calculate, what I'll be doing right here is I'll be calculating the rate constant for the first order reaction. Then after getting the rate constant, I can simply apply that rate constant value in the half-life expression. We'll be done with the question. Yes. Now people, have a look. What I'll be doing right here is I'll write something like this. K is equal to 2.303 divided by T2 minus T1. Yes, divided by T2 minus T1. T2 minus T1 is 20 minus 10, that is 10. Correct? Log of AT1 divided by AT2. But instead of AT1 by AT2, I'll be using simply R1 by R2, the second expression which I gave you right here. Yes? Correct? So it's going to be R1 divided by R2. R1 value is given as 0.04. R2 value is given as how much? 0.03. Correct? Can I say it's simply going to be equal to 4 by 3? Okay. I'm simply going to write it as 4 by 3. Now people, there is only calculation part left. Okay. There is only small calculation part left right here. And what that calculation part is going to be, I'll write K is equal to, it's going to be simply 0.2303 and log of M divided by N is going to be simply log of M minus log of N. Yes. I hope you remember the values of log 4 to the base 10 and log 3 to the base 10. It's going to be K is equal to 0.2303 multiplied by log 4 is simply 0.6, log 3 is 0.47, and the value is going to be simply equal to what? The value is going to be what? Just people, let me know the exact value of K from here. What you are getting. Let me know the exact value of K which you are getting right here. Let me know the exact value of K which you are getting right here so that I can move ahead fast. What is the exact value of K you are getting right here? Let me know in the chat box fast. Okay, till then, I'll tell you one more thing. You just do it. Okay, Shaista is saying K value is coming as 2.88 into 10 power minus 2. Is that? K value is coming as 2.88 into 10 power minus 2. Yeah. So people, K value, you are getting it as how much? 2.88 into 10 power minus 2. So I'm going to write it as 2.88 into 10 to the power minus 2 over here. Yeah. And people, what are going to be the units of this rate constant right here? It's going to be second inverse because it's a first order reaction. Correct? I got the value of K. What was I supposed to calculate? I was supposed to calculate half-life. Can I say half-life of this reaction is simply going to be 0.693 divided by K, and K value we got it as 2.88 multiplied by 10 power minus 2. Just calculate this value. Let me know the exact answer of it. You are getting it as 24 minutes. Yes, after solving this, you are getting it as 24 minutes. So I got the half-life of the first order reaction as 24 minutes right here. I hope this is clear to every single guy. Let me know in the chat box. So that I can move on to one more concept, one more important concept. Yes. Wonderful. Great. यादव, मैं कश्मीर से हूँ यार. इंग्लिश चैनल है इसलिए हिंदी में बात नहीं कर सकता, वरना हिंदी में ही बात करता हूं मैं. Okay, should we move on? Yeah? Exactly, right? Okay, let's move on then. People, this is one nice question right here which is on your screen. Let's try to do this question over here. These are basically two questions, right? These are basically two questions which are given to us. See guys, as per the question, you have to understand few basic things, okay? Whatever things we have covered in this chemical kinetics till now, I'm going to use those first order things in this question, okay? It's a very simpler one and proper. If 6.2 grams of NH2NO2 is taken, calculate time taken to complete 99% of the reaction. Second part, calculate the volume of dry N2O produced at STP, and I'm given with the half-life of the reaction as 2.1 hours, yeah? This is something which I'm given with. I'm given with the half-life of the reaction as 2.1 hours, correct? Yes, and people, this is the first order reaction which is given to me, okay? This is the first order reaction which is given to me. Now, first thing, what I'll be doing, I'll be writing something like this. Half-life of the reaction, we know that is 0.693 divided by what? Divided by K, or I can say K is going to be, instead of 0.693, just in order to avoid a lot of calculations, I'm going to write 0.7 instead of 0.693 divided by T half is given to us as 0.1. So the value of K is going to be 1 divided by 3 hours, yeah? 1 divided by 3 hours inverse, yeah? This is the value of rate constant which I got right here, yes? Yes? Deep, it is skipped in the question. It's skipped in the question. In the question, it will be mentioned right here. As per this question, it will be mentioned, it's the first order, yeah? Since we are right now talking about first order, इसलिए मैंने question में कहीं identify नहीं करा first order, because the lecture is of first order only, yeah? Yes? Soheb, you can do one thing. You can go to the previous session of the kinetics in which we have talked about first order reactions in detail. That I have done in last session, okay? And that took me more than 1 hour, bro. Okay? Now, let's move on. Let's move on. I got the value of K, right? I got the value of K. Correct? What am I supposed to calculate? I'm supposed to calculate time taken to complete 99% of the reaction, right? Can I say when 99% of the reaction would have got completed, when 99% of the reaction would have got completed, can I say at that time I'll be having 1% of reactant still left in the container? Yeah, I can say that. Absolutely. Right? See guys, I'm supposed to calculate time taken to complete 99% of the reaction. Correct? Or I can say something like this. I can say something like this. When 99% of the reaction would have got completed, at that time, 1% of reactant would be there in the container. Yes? Correct? Now we will see what I'll be doing. See. I'm going to write simply like this. I'm going to write T is equal to, I'll be writing something like this. Time taken to complete 99% of the reaction is going to be equal to 2.303 divided by K. K value we got, what is that? That is 1 by 3. Multiplied by log of initial concentration of reactant, which is A naught, divided by concentration of reactant left when 99% of the reaction would have got completed. At that time, I'll say 1% of the reactant would be left in the container. 1% of A naught means what? 1 divided by 100 into A naught. Right? 1% of A naught will be left in the container. Yes. Now guys, this A naught got cancelled. This 100 came up. 100 means 10 square. 10 square means log of 10 square means 2 log 10. So it's simply going to be like this. Time taken to complete 99% of the reaction is going to be, take this 3 up, it's going to be 2.303 multiplied by 3. Yes. And it's going to be log of 10 power 2. This A naught cancel. Log of 10 power 2 means 2 log 10. Log 10 is 2. So simply multiplied by 2. Let me know its exact value which you are getting right here. Let me know its exact value which you are getting right here. Yeah. You are getting it as 12.36. Is that? Okay, a lot of people are saying 13.86. Okay, let me go with the common thing. It is 13.8. All right. I got the time taken to complete the 99% reaction is going to be 13.8 hours. So first part of the equation is done. Time taken to complete 99% of the reaction is 13.8 hours. Yes, first part of the equation is done. Now, what about the second part of the equation? What about the second part of the equation? How to solve the second part of the equation? See guys, it's very simple. Understand. Okay, I'm going to erase this part. I hope this is clear till here. Yeah. Now, volume of dry N2O produced at STP. I'm supposed to calculate the volume of N2O which is produced at STP. Yes, yes, yes. That's what I have to do. Correct? Correct? Yes. Now people, can I say initially at time t is equal to 0, at time t is equal to 0, I'm given with 6.2 grams of NH2NO2. Yeah. Can I convert this into moles? Can I say I have got 6.2 mass of NH2NO2 divided by molar mass of it, that is 62. Can I say initially I have got 0.1 moles of NH2NO2? With me? Yes. So initially at time t is equal to 0, I'll be having 0.1 moles of NH2NO2 in the container. This is going to be 0. This is going to be 0. Absolutely. Right? Now what is mentioned in the question? 99% of the reaction is getting completed. Yes. So I'll say out of 0.1 moles of NH2NO2, 99% of it is getting converted into products. So can I say when 99% of the reaction would have got completed, can I say I'll be left with 0.1 minus 99% of 0.1 moles of reactant in the container? Yes, I can say that. I can say that. Say it's mentioned in the question, 99% of the reaction is getting completed. That means 99% of the reactant has got converted into products. Yes. Now people, if 1 mole of reactant gives 1 mole of N2O, can I say 99% of 0.1 moles will give 99% of 0.1 moles of N2O, which is going to be 99 divided by 100 multiplied by 0.1 means 1 by 10. So it's going to be 0.099. Can I say the number of moles of N2O which are getting formed when 99% of the reaction is getting completed is 0.099? But am I supposed to calculate the moles of N2O which are getting formed when 99% of the reaction is getting completed? No. No, right? No. I'm supposed to calculate volume of N2O which is getting produced at STP. Yes, I got the moles of N2O which are getting produced. Now, how do we convert moles into volume at STP? We know I'll be writing something like this. Volume of N2O which is getting produced right here is going to be equal number of moles of N2O which are getting liberated 0.099 multiplied by 22.4, and the answer is going to be liters. Let me know its exact value which you are getting right here. Let me know its exact value which you are getting right here. Let me know fast. It is 2.2 liters. Yes, absolutely. So I will say something like this. 2.2 liters of N2O gas will be getting liberated when 99% reaction will be getting completed. Yes, which is what we were supposed to calculate. Let me know in the chat box if it is clear to everyone. Yes, so that I can move on to one more nice question. Yeah. Exactly, guys. 2.2 liters of N2O would be getting liberated when 99% reaction would have got completed. Yeah, which is what we were supposed to calculate from the question, right? शफात इलेक्ट्रोकेमिस्ट्री तो कब की हो गई यार? प्लेलिस्ट में जाओ, इलेक्ट्रोकेमिस्ट्री ढूंढो, तो कब की होगी? उसका एक सेशन बचा है कॉल रॉसला, दैट्स इट. बाकी पूरा डस्टेड ब्रो. गुड लक दीप, गुड लक, गुड लक, गुड लक. Agar paper, tomorrow is your paper, right? So you should sleep, bro. You should sleep. Just have some good sleep. Should we move on? Should we move on to the next one, guys? I'm going to take extra time today, okay? So you have to bear with that. I'm going to take maybe 20 minutes extra than our normal session. Yeah? Scene is saying how 22.4. At STP, if you want to convert moles into volume, you have to multiply by 22.4. Yeah? Yes? Wonderful. Let me move on, guys. Let me move on to one more question. This is one more question on your screen. Yeah? This is one more question on your screen. Let's kill this question as well. At what time will the molar ratio of ethylene to cyclobutane be 1? Yes. At what time will the molar ratio of ethylene to cyclobutane be 1? That's what I'm supposed to calculate. I'm supposed to calculate the time at which the molar ratio of these two becomes equal to 1. Yes. See guys how I'll be approaching to this sort of equation. Understand. I'm given the reaction, and the reaction is C4H8. C4H8, it gives what? It gives 2 times C2H4. It gives 2 times C2H4. This is something which is given to me. Yeah. Let's assume at time t is equal to 0, I have got A moles of this reactant right here. Let's say at time t is equal to 0, I have got A moles of cyclobutane right here. Yes. So I'll say at time t is equal to 0, I'll be having 0 moles of product. Yes. Let's say X moles of reactant is dissociating right here. So I can say at time t, the moles of reactant left is going to be A minus X. And how many moles of product would have got formed? I'll say 2X by simply using the stoichiometry. 1 mole gives 2 moles. So X moles are going to give me 2X moles right here. Yes. Now people, Let's assume at this time t, the molar ratio of ethylene to cyclobutane, it is getting equal to 1. Let's say at time t, the molar ratio of these two is equal to 1, correct? And I'm supposed to calculate the value of t. This t I'm supposed to calculate. I'm supposed to calculate at what time will the molar ratio of these two be 1. Yes? People, I'm assuming at this time t, the molar ratio of molar ratio of ethylene to the cyclobutane is becoming equal to 1. Yeah. So if molar ratio is becoming 1, what does that mean? That means 2x divided by a minus x is equal to 1. Correct? So I can say at time t, 2x divided by a minus x value is equal to 1. Correct? What I can conclude from here, can I say 2x is simply going to be a minus x, or I can simply say x is equal to a divided by 3. X is equal to a divided by 3. So at this time t, when the molar ratio of these two is equal to 1, I can say at that time x value I got to know as a by 3. Correct? Now I'm supposed to calculate at what time will be the molar ratio of these two equal to 1. I'm supposed to calculate at what time will be the number of moles of reactant and product equal to 1. Yes, that's what I'm supposed to calculate. Now for that I'm going to use the integrated rate equation. Yes, I can say T is equal to 2.303 divided by K. K value is given to me as 2.3 into 10 power minus 4. It's 2.3 into 10 power minus 4. It's going to be log of. Initial moles are equal to A. Initial moles of reactant, that's A, divided by number of moles of reactant left at time t, which is A minus X. Yes, it's going to be A minus X value I got to know as A by 3. Yes, X value I got to know as A by 3. Now the question is done and dusted, right? This and this approximately got over. So I can say T is going to be 10 power 4. It's going to be log of. Over here in the denominator, I'm getting 2A divided by 3. A got cancelled, so it becomes 3 divided by 2. Yes. So T is equal to 10 power 4. Now use the property of log. It's going to be log of m minus n. Log of m minus log of n. Correct? So T value I got to know equal to 10 power 4. Log of 3 you must be knowing 0.47. Log of 2 you must be knowing 0.3. So the time value I got to know as 0.17 multiplied by 10 power 4. Yes, and is the time given in seconds? Yes, people. I can say after these many seconds, after 1700 seconds, I will say the molar ratio of these two have become equal. I can say after 1700 seconds, the number of moles of reactants have become equal to the number of moles of products, which I was supposed to calculate. Let me know in the chat box. Let me know in the chat box if you got the concept, so that I can move on and talk about a few more interesting things. Let me know in the chat box fast. वेनु यार अभी तो ये सीरीज खत्म नहीं हो रही है. Let's see bro, I'll come up for that soon, okay? Just wait for that. Something or the else I'll come up with, okay? I'll be coming up with the mock test series. Wonderful. Let me have some water first. Yeah. So people, let me know in the chat box. Vinu bro, what I'm saying is I'll be coming up with one more series soon, okay? Just let me finish this off first. Should I move on? Should I move on? Yeah? That's great, Yashwant. Thank you, Shoaib Nabi. Thank you. Okay. Let's move on then. And people, this is one more nice question I must say. Okay? This is one more nice question I must say. Should I be solving it or should I be giving this as the homework? What do you think? Should I be solving it right now or should I keep this as homework? Let me know in the chat box. You want me to solve it or should I be keeping this as the homework? there is one nice concept, a small concept involved in this, where you can mess up. Where you can mess up. I think I should solve it, guys, because I think you'll mess up in this question. Yeah? Yeah? Now tell me fast, tell me fast. Tell me fast, tell me fast. I'll solve it, okay? I'll solve it, guys. Have a look. I'll solve it. See, on reacting with 0.1 moles of A in a, it's not reacting on reaction, okay, 0.1 moles of A in 2 liter vessel. So people see, I'm given with the reaction and at time t is equal to 0, I'm given with 0.1 moles of reactant, yes? So this and this will be 0 at time t is equal to 0, correct? Correct, correct. This is something which is given to me. Initially, I've got 0.1 moles of A in a 2 liter vessel. So this reaction is taking place in a container whose volume is 2 liters, yes? Find the concentration of A after 250 seconds. Find the concentration of A after 250 seconds. Find the concentration of A after 250 seconds at same pressure and temperature. First of all, is it one homogeneous gaseous phase reaction? Absolutely, it's one homogeneous gaseous phase reaction right here. Yes, it's one homogeneous gaseous phase reaction right here. Yes, because every reactant and product right now is in gaseous phase over here. Yes. Now people, at time t is equal to 0, I'm given with 0.1 moles of A. I'm given with 0.1 moles of A, correct? What am I supposed to calculate? I'm supposed to calculate the concentration of A after 250 seconds. Concentration of A after 250 seconds, right? First thing which I'll be doing right here is, see, just by having a look on the unit of rate constant right here, I can say this reaction is of the order first, yeah? This reaction is of the order first, correct? So people, if this is the first order reaction, can I calculate its half-life? Yes, it's going to be 0.693 divided by K value, which is given to us 2.772 into 10 power minus 3. People, when you'll solve this value, you'll get it as 250 seconds. You'll get it as 250 seconds. You'll get the value as 250 seconds. You'll get the half-life as 250 seconds, yeah? When you'll solve this up, right? What am I supposed to calculate? Find the concentration of A after 250 seconds. So am I supposed to calculate the concentration of A at half-life? Yes, yes, I can say that. I got to know half-life of this reaction is 250 seconds. And what I'm supposed to calculate from the question? Calculate the concentration of A after 250 seconds, right? So I'm going to calculate the concentration of reactant A at half-life, yeah? When 50% of the reaction will have got completed, correct? Exactly. So people, at half-life, or I'll say at 250 seconds, I'll say out of 0.1 moles of A, 50% of it would have got converted into product. 50% of this amount would have got dissociated. So I'll be left with exactly half of it. This is going to be these are the number of moles of reactant left at half-life of the reaction at 250 seconds. Correct? At 250 seconds. Yes. So you got the number of moles of reactant. You got the number of moles of reactant left at time t is equal to 250 seconds. What am I supposed to calculate? I'm supposed to calculate concentration of A left after 250 seconds. Yes, we know concentration is number of moles divided by volume. So concentration of reactant A left is going to be equal to number of moles of reactant left at time t is equal to 250 seconds, which is 0.1 divided by 2 divided by volume is 2 liters. So if you think this is the answer, you're absolutely wrong. You're absolutely wrong. Yeah. If you think this is the answer, you're absolutely wrong. Why is that? Have a look. See guys, I got the number of moles of reactant left at 250 seconds. I got the number of moles of reactant left at half-life of the reaction. Yes. People, can you let me know how many moles of B would have got formed right now when 50% of the reaction would have got completed? I'll say 1 mole gives 1 mole. So it's going to be 0.1 divided by 2. Correct? Because 50% of this amount is getting converted into products. Yeah. Yes. Similarly, 1 mole gives 2 moles. So 0.1 divided by 2 moles will give 0.1 moles. Yes. Correct? Now people, is this a homogeneous gaseous phase reaction? Is every reactant and product present in gaseous form, and this reaction is taking place in a container? Yes. And the pressure and temperature of the container, pressure and temperature of the mixture is kept fixed, right? So people, just have a look. At time t is equal to 0, how many total moles were there in the container? Can I say at time t is equal to 0, there were 0.1 moles totally present in the container? Yes. Now after 250 seconds, are the number of moles in the container changing? Yes, number of moles are changing. And the reaction is taking place at constant pressure and temperature. Can we say at constant pressure and temperature, volume of gas is directly proportional to number of moles? We know that. So if number of moles are changing, can I say volume of the system will be also changing? Yes. Correct? Volume of the system will be also changing. Correct? So people, what I'll be doing right here? Can I use this equation V1 divided by V2 is equal to N1 divided by N2, which is valid at constant pressure and temperature? Yeah, as per Avogadro's law, if you remember. First thing, what is the initial volume? What is the initial volume of the system given to me? It is 2 liters. Now I'm going to calculate the final volume of the system. V2 is equal to N1. N1 is the total moles present in the container at time t is equal to 0, which is 0.1, divided by N2 are the total moles present in the container. N2 is the total moles present in the container at time t is equal to 250 seconds, which is going to be 0.1 by 2, 0.1 by 2, 0.1. So this is going to be simply 0.2, correct? It's going to be 0.2. So can I say V2 value, final volume of the container, final volume of the system, I got how much? I got it as 4 liters. Yes. Now people, this is the final volume of the system. Correct? Correct? This was the concept right here. You were not supposed to divide these moles of reactants by 2 liters. You are going to divide this by final volume of the system, which is going to be 4 liters. So I'll say concentration of reactant A left after 250 seconds, left after half-life of the reaction is going to be 0.1 divided by 8. Yes, this is going to be the concentration of reactant left moles liter inverse. Yes, after 250 seconds. Correct? Similarly, this is going to be the concentration of B formed at half-life of the reaction. Similarly, this is going to be concentration of C formed at the 250 seconds of the reaction. Yes. Let me know in the chat box if you got the concept. Yes. Let me know in the chat box if you got it. Let me know. Wonderful. So the concept over here, what was the concept all about? Concept was, since the reaction was taking place at constant pressure and temperature, and we know at constant pressure and temperature, volume is directly proportional to moles. If moles in the container will be changing, volume of the container will be also changing. Initially, the total moles in the container were 0.1. Finally, the total moles in the container were 0.1 by 2 plus 0.1 by 2 plus 0.1. That means 0.2. So moles in the container were changing. That means volume of the container would have changed at the same time. Yes. Right? So I was supposed to calculate the final volume of the system, then divide the moles of reactants which were left by the final volume of the system. Yes. Correct? Correct. Good morning. Is it 12? Wonderful. It's 12. Just a second, guys. Okay. Should I move on? Let me know in the chat box. Yeah? All right, let's move on then. Let's move on. This is one more topic, guys, which we are going to cover right now. Okay, rate constant for a first order gaseous reaction. This is one more important topic right here. Okay, and what this topic is all about, understand properly. See, let's say, guys, I've got one homogeneous gaseous phase reaction. Let's say I've got one homogeneous gaseous phase reaction. Let's say A gas, it gets converted to B gas plus C gas. Yes. This is one homogeneous gaseous phase reaction which is of the order 1. Yeah. The order of the reaction is 1. This is the first order reaction which I have. Its rate constant is equal to K. Yeah. Now people, this reaction which will be taking place in a container, absolutely right. Let's say at time t is equal to 0, we know at time t is equal to 0 there'll be only reactant in the container, there'll be no product. Yes, so whatever pressure will be there in the container, that will be due to A at time t is equal to 0. Let's assume the pressure due to A is P naught. Let's say the pressure due to A is P naught. What is going to be the pressure due to B? It's going to be 0. What is going to be the pressure due to C? It's going to be 0. Yes, correct. And this reaction, this homogeneous reaction, it is taking place at a constant temperature, I'm assuming right here. Yes. Now see guys, now people, at any time t, let's assume the pressure due to A is P naught minus X. I'm going to treat these pressures in the same way which I used to do with the moles. I'm going to treat these pressures in the same way as that of moles. So it is going to be P naught minus X. This is going to be X. This is going to be X. What is this P naught minus X? P naught minus X is the pressure due to A at time t. X is the pressure due to B at time t. This X is the pressure due to C at time t. Yes, correct. Now people see. Can I say when the reaction will start continuing, the reaction is continuing, the products are getting formed, reactants are getting consumed, yeah? Can I say there'll be a time when the reaction will be 100% completed? But this is a first order reaction, and first order reaction takes infinite time to get completed, yes? So at time t is equal to infinity, if you remember, at time t is equal to infinity, can I say the pressure due to reactant will be 0? Yeah? Yes, I can say that, correct? Now we will see 1 mole gives 1 mole, so the pressure due to be at infinity is going to be P naught because entire reactant has got converted into product. Yeah, so 1 mole gives 1 mole, so P naught will again give P naught. Yes, correct, I can say that. Now guys, understand, if I ask you initially what was the total pressure of the container, initially at time t is equal to 0, the total pressure of the container was P naught. P naught is the initial total pressure of the container. If I ask you what will be the total pressure of the container at time t, which I'm representing by Pt, which is going to be equal to this term plus this term plus this term. Yes, when you add them up, it's going to be P naught minus X. Sorry, P naught plus X. Yes. So what is Pt? Pt is the total pressure at time t, total pressure of the container at time t. Yes. Yes. Now people, if I ask you what is going to be the total pressure at infinite time, P infinity, yes, what is going to be that? That's going to be P naught plus P naught. That's going to be twice P naught. Yes, this is something which I got right here. Now you need to remember a few important things right here. Okay, what is that going to be? Understand properly. See guys, first of all, I'm going to erase this part. The first thing which I'm doing, I'm going to get the rate constant expression of this gaseous phase reaction in terms of, I'm going to get the rate constant expression in terms of P naught and Pt. I'll be getting the rate constant expression of this gaseous first order reaction which is taking place at constant temperature in terms of P naught and Pt. Correct? What I'll be doing, I'll be writing K is equal 2.303 divided by time interval, that is T. It's going to be log of, it used to be initial concentration A naught, but instead of initial concentration of reactant, I'll be using initial pressure of reactant P naught divided by, it used to be concentration of reactant left at time t, but now I'm going to use the term the pressure of reactant left at time t, which is P naught minus X. So right here, I'm going to get the rate constant value K in terms of P naught and Pt. Yes. People, have a look. Can I eliminate X from here? Can I say X is simply going to be equal to Pt minus P naught? This is the value of X which I got. Yeah. This is the value of X. So just replace this value of X. It's going to be, X is going to be Pt minus P naught. X is going to be Pt minus P naught right here. Yes. So I got the rate constant expression, which you're not supposed to remember. You should know how to make this sort of expression. You're not supposed to remember this expression, okay? It's going to be log of, it's going to be P naught divided by, it's going to be P naught minus plus, so it's going to be twice P naught minus Pt. So I got the rate constant expression of the first order gaseous phase reaction, which is given to me in terms of P naught and Pt right here. This is the first thing which you must know, how to make this sort of expression for a first order gaseous phase reaction in terms of P naught and Pt. It is sometimes asked like this. Calculate the rate constant of the gaseous phase reaction in terms of P naught and Pt. Okay, these sort of questions are also asked. Okay, now the second thing. What I'll be doing is, the second part of the question is going to be, I'm going to get the rate constant of the same reaction in terms of Pt and P infinite. Okay, I'm going to get the rate constant expression for the same reaction in terms of PT and P infinite. This is the rate constant expression which I got in terms of P naught and PT. Yeah. Yeah. So people, what I'll be doing, I'm erasing this part again. Now the second part of the question is going to be, I'm going to get the rate constant expression for the same reaction in terms of PT and P naught. In terms of PT and P infinite. Yes. What is P infinite? P infinite is the total pressure at the completion of the reaction. When I assume 100% of the reaction is getting completed, which will get completed in infinite time. Yes. Because first order reaction never undergoes 100% completion. Yes. Right? Now we will see. Can I say at the completion time, the total pressure is going to be twice P naught, which I told you a few minutes back. So can you get the value of P naught from here? P naught is going to be simply P infinite divided by 2. It is going to be simply P infinite divided by 2, correct? Yes. Now people, I'm going to write the expression for rate constant. It's going to be K is equal to 2.303 divided by T. It's going to be log of, it used to be initial concentration of reactant, but instead of initial concentration of reactant, I'm going to use the term initial pressure of reactant P naught. Divided by, it used to be concentration of reactant left at time t. Now I'm going to use pressure of reactant left at time t, which is P naught minus X. But I have to make this expression in terms of PT and P infinite. I do not need these terms, these P naught and X values right here. So what I'll be doing, I'll be just replacing these values. So I'll say K is equal to 2.303 divided by T. It's going to be log of P naught. Instead of P naught, can I write P infinite by 2? Can I write P infinite divided by 2? Correct? Divided by, instead of P naught, again I'm writing P infinite divided by 2. Minus, instead of X, I'll be writing PT minus P naught, but instead of P naught, again P infinite by 2. Yeah. So I got the expression of K, I got the expression of rate constant for this gaseous phase reaction in terms of what? In terms of P infinite and PT. So it's actually going to be equal to, K will be equal to, it's going to be 2.303 divided by T, log of, I'll be writing it as P infinite divided by 2, P infinite divided by 2, correct? Multiplied by, this is P infinite by 2, this is P infinite by 2, so it's going to be P infinite, it's going to be P infinite minus what? Minus PT. Yes. So people, you got the rate constant expression for this first order gaseous phase reaction in terms of P infinite and PT, which I was supposed to calculate. This is something which is sometimes asked in your examination. Calculate the rate constant of a first order gaseous phase reaction in terms of P infinite and PT. Yes. Yes. Got it? Let me know in the chat box if it's clear. Let me know so that I can move on to a few more important things. Do hit the like if you got it. Yes. Wonderful. So now let me show you what sort of questions are asked. Junaid, you can take the video a little back. It will be automatically a replay. You can watch it out again, okay? No issues. Right? Okay. Now we will see what kind of questions are asked from here. The question which I've come up with right here is, see, in the earlier case which I showed you, in the earlier case, the stoichiometry was 1:1:1. Now there is stoichiometry involved in the reaction 2:3:1, 2:3:4. So these are basically two questions, right? These are basically two questions. And in the same way I'm going to solve this question. I'm going to get the rate constant of this gaseous phase reaction first in terms of P naught and PT, then in terms of PT and P infinite. Yeah, that's what I'll be doing. Right? See guys, what I'll be doing. My reaction which is given to me as, that is 2A gas. 2A gas, it gives what? 2A gas gives 3B gas plus what? Plus 4 times C gas. This is the reaction which is given to me, correct? Let's assume at time t is equal to 0. The same way I did in the previous one, I'm going to do in the same way, yeah? At time t is equal to 0, let's say the pressure due to A is P naught. This is going to be 0, this is going to be 0, correct? Now at time t, what is going to be the pressure due to A? Let's say that is going to be P naught minus X. Yeah? Now we will see. 2 moles of A gives 3 moles of B. 1 mole of A should give 3/2 moles of B. So X moles should give what? 3 by 2 multiplied by x. As I told you, I'm going to treat these pressures in the same way as I used to do for moles. Yeah. I treated the pressures in the same way as of moles. Yeah. What is this 3 by 2x? This is the pressure. This is the pressure of the container due to B. This is the pressure of container due to B. Yeah. Yes. Now we will similarly. 2 moles of A gives 4 moles of C. So 1 mole of A should give 2 moles of C. So x moles should give 2x moles. But is this 2x? Are these moles of C? These are not moles of C. This is the pressure of C at time t. Yeah. Correct. This is the pressure of C at time t. Right. Now people, if I ask you like this, if I ask you what is the total pressure of the container at time t, can I say total pressure of the container at time t is going to be pressure due to A plus pressure due to B plus pressure due to C. It's simply going to be equal to P naught minus x plus what? Plus 3 divided by 2x plus what? Plus 2x. Yes, this is going to be the total pressure at time t. This is going to be the total pressure of the container at time t. I can say that, right? Right. Now we will do one thing. Just do a little bit of calculation. It is Pt minus P naught. Pt minus P naught. Just take the 2 as LCM. Just take the 2 as LCM, right? It's going to be minus 2x plus 3x plus 4x. Yes. So I got something like this. Pt minus P naught is equal to, right? It's going to be x plus 4x, that is 5x divided by 2. So people, can I get the value of x from here? X will be simply equal to 2 divided by 5. X will be simply equal to 2 divided by 5 multiplied by Pt minus P naught. Yes. I got the value of x. Now can I simply write the expression of rate constant? I can do that. I can say K is equal to 2.303 divided by T. It's going to be log of, it used to be initial concentration of reactant, but now it'll be what? Initial pressure of reactant, which is P naught, divided by it used to be concentration of reactant left at time t, but I'm going to write the pressure of reactant left at time t, which is P naught minus x, and instead of x I've already got it as 2 divided by 5 multiplied by what? Multiplied by Pt minus P naught. Correct? Yes, you can say that, right? Yeah. Yes, exactly, guys. So you just need to shuffle it a bit. You just need to arrange it a bit. You are done with the integrated. I mean, you're done with the calculation of rate constant right here. Yes. Okay. So what I'll be doing, I'll be simply just writing it properly. It's going to be K will be equal to 2.303 divided by what? Divided by T. It's going to be log of. It's going to be P naught divided by C. This is P naught, and this is what? This is 2 by 5 P naught. So it's going to be P naught plus 2 divided by 5 P naught plus 2 divided by 5 P naught minus 2 by 5 Pt. Yes, this is something which I got. Right here. Correct? Yes? Right? Right, guys? Right. Let me know in the chat box if it's clear. Yeah, or simply you could have done like this, just remove this part in the denominator, just do the cross multiplication. It's going to be 5 times P naught minus 2 Pt plus 2 P naught divided by 5. That 5 is going to come up. Yes, it'll be like this. Correct? So finally, the expression of K in terms of P naught and Pt is going to be 2.303 divided by T. It's going to be log of 5 P naught divided by 5 plus 2 means 7 P naught minus 2 times Pt. This is the expression of K which I was supposed to calculate for the reaction in terms of P naught and Pt right here. Let me know in the chat box if it's clear to everyone. Yeah? Let me know in the chat box if it's clear to everyone. There is one part of the question still left. That is the calculation. In terms of Pt and P infinite. Yeah. Now see how that part of the question is to be solved. Understand what I'll say, okay? Understand properly what I'll say. This part of the question is done, right? So people, I got the value of x. If you remember, that used to be equal to 2 divided by 5 multiplied by Pt minus P naught. Was it like this? Was it Pt minus P naught ki P naught minus Pt? Was it Pt minus P naught ki P naught minus Pt? Can you let me know in the chat box? The value of x which we calculated. Was it like this? Or was it P naught minus Pt? Okay, fine. Great. Now, people, when the reaction will continue, can I say there'll be a time at infinite, there'll be a time, okay, at which the pressure due to A will be 0 because entire reactant would have got converted into products. That's what we call as completion time. At completion time, entire reactant would have got converted into product. Yes. So, 2 moles of reactant, 2 moles of A gives 3 moles of B. 1 mole of A should give 3 by 2 moles of B. So, pressure due to A should be equal to 3 divided by 2 P naught at the end of the reaction. Yes. Similarly, 2 moles gives 4 moles, 1 mole gives 2 moles, so P naught moles should give 2 P naught. So this 3 by 2 P naught, this is the partial pressure of B at time t is equal to infinity at the completion of the reaction. This is the partial pressure of C at the completion of the reaction. Yes? Right? So people, can you let me know what is going to be the total pressure at the completion of the reaction? Total pressure at the completion of the reaction is going to be this plus this plus this. Yes? It's going to be 3 divided by 2 P naught. 3 divided by 2 P naught plus 2 P naught. Yes. Can I say P infinity is going to be equal to 3 P naught plus 2 P naught? That's going to be simply 7 P naught divided by 2. Or I can say P naught is equal to 2 divided by I can say P naught is equal to what? Just give me a second, guys. Yeah, I can say P naught is equal to 2 divided by 7 P infinity. Yes? Yes? Now guys, I'm again going to use the rate constant expression. Yeah? I'm again going to use the rate constant expression. What is my rate constant expression? That is simply K is equal to 2.303 divided by T. Yes? Divided by T. It's going to be log of, it used to be initial concentration of reactant, but now it's going to be initial pressure of reactant divided by pressure of reactant at time t, which is P naught minus X. But right now I need the expression of K in terms of P infinite and PT. I do not need the expression of K in terms of P naught, right? So what I'll be doing right here, I'll just substitute the values. K is going to be 2.303 divided by T. It's going to be log of. Instead of P naught, what should I write? I should write 2 divided by 7 what? 2 divided by 7 P infinite divided by, instead of P naught, 2 divided by 7 P infinite minus, instead of X, I should be writing, just a second, instead of X, I should be writing 2 divided by 5 multiplied by PT minus P naught, PT minus P naught already we know that is 2 divided by 7 P infinite. Just arrange this equation, you'll be getting it. You'll be getting the rate constant in terms of PT and P infinite. Yes? Let me know in the chat box if you got to know how to write the rate constant expression for a gaseous first order reaction in terms of number 1, P naught and PT, number 2, that is PT and P infinite. Yeah? Let me know in the chat box if you got to know. Let me know if you got to know, guys. Yes? Clear to everyone? Okay, so people, this is the question which is going to be your homework. Okay, this is the question which is going to be your homework. You are going to let me know answer of this question in the comment box. Okay, do let me know the answer of this question in the comment box. Right? This is the question on your screen. Just take the screenshot. Okay, I want you guys to give it a try and let me know the answer of this question in the comment box. Okay, so first thing, you are going to calculate the order of the reaction. I have no idea how you will be calculating that. Okay, then half-life and T75. In the last session I gave you direct relations between half-life and T75 as well. Then at the end, rate constant expression. Yeah, correct? Exactly, Farooq. Legends will be coming to the comment section. Exactly. Okay. And at the same time, this is one more question as your homework. One more question as your homework. Yes, Shakir, that's enough. This is one more question. Basically, you have got 2 questions as the homework, guys, and you can easily solve these 2 questions if you have watched the entire session properly right here. हाँ Rajneesh, class regularly 11 बजे होती है. Yes. Okay. So people, with this, our today's session is over. We are done with the kinetics of the first order gaseous phase, homogeneous gaseous phase reactions. Yes. And people, for the ones who joined us late, let me tell you few things about this NEET 2021 crash course, which we have started on the actual Vedantu platform. So people, if you want me to personally train you in your chemistry, if you want us, the mentors in this channel, to personally train you for the upcoming NEET 2021, you should get enrolled in this crash course right here, okay? In this crash course, what all things we are going to get? In this crash course, we'll be covering your whole syllabus on the actual Vedantu platform. Apart from that, there will be separate sessions on the time management, on the tips and tricks to do the questions in lesser time. Yes, and at the same time, guys, it's going to be a two-way learning interactive platform wherein you can ask your doubts anytime to your master teachers. Yes, and people, it's not only about the course completion, it will be about the test series and mock tests as well, by means of which you'll get to know your performance by comparing it with the other students across the country. Yes, so people, how to get enrolled in this crash course? You just have to click on the Vedantu app. Okay, after clicking on Vedantu app, just click on the NEET crash course, and after clicking on NEET crash course, you just have to use the coupon code as WSCC21. On using this coupon code of WSCC21, you will be getting 20% off right here. Yeah, right? So you'll be getting 20% off, and in just 8K, you are getting enrolled in this crash course in which your whole syllabus is getting completed. And apart from that, test series, everything which will be included, and you'll be mentored by us personally. Yeah. So there is a link in the description box of the video. You can click on that link and get enrolled. And people, get enrolled soon so that you can shoot the bullseye with us. Yes, and at the same time, there is one more link in the description box of the video, that is for the Telegram. Okay, do click on that link as well, get added to the Telegram group and stay updated about the classes. Yes, okay, and for the ones who have not liked the video yet, do like the video, share and subscribe to the channel at the same time so that everyone gets benefited out of these sessions. Yes, so people, this was all from my side in the today's session. I hope you would have enjoyed the session. I enjoyed the session. It was a little bit complex session, I must say. Yeah. Yes, but anyways, I liked it. Yes, थोड़ा बहुत tough था, right? Tough लगा? Yashwant is saying the Josh is still high. Yes, Shakir, exactly. Do hit the bell icon so that you get the notifications of every session right here from this channel, okay? So I'll see you guys tomorrow again at 11 p.m. And tomorrow we are going to talk about the kinetics of reversible and parallel first order reactions. Yes, so people, till then, you guys take care. Bye-bye. God bless you all. Love you all. Stay safe, okay? I'll see you guys tomorrow again at 11 p.m. Take care, guys. Bye.